Good evening, everybody. Today we are going to discuss sine PWM mathematical analysis. Before going to that discussion, in the last class I have discussed unipolar and bipolar concept. So in unipolar, why the output frequency is double? So this is one of the questions asked for one student. So, but of course I already clearly discussed. So again I'm discussing. You just listen. So this is the output voltage. So this output frequency is double than that of your bipolar scheme. Very simple. I will explain now. See here. Here, how many pulses are there? This one is only one pulse. For one pulse, here how many output pulses are there? Two output pulses. So that's why we can say that it is a double that of your bipolar scheme. Now, otherwise you can see this is VAN, this is a VBN, right? So when you are having VAN, VBN, how you are getting output voltage V0? VAN minus VBN. So here VAN minus 0, you will get the pulse. But here what happens? VAN minus again this VBN. So this is VS, this is also VS. So VS minus VS, it is 0. Now again here what happens? VS again 0. Now you will get the output voltage. So like this, for this pulse, also you can say that these two pulses we are getting. So because of this one, this is advantage. Because of two pulses, what happens is your output frequencies increases, lower THD, and filter size is going to be reduces. Right. So okay, this is about the why you are getting two pulses per half cycle. Right. That is the twice that of the output frequency is twice that of the bipolar sphere. Okay. So next we will go for next one. This one, which is called as this one. Uh, Last class we have discussed in multiple pulse width modulation shortcut, right? In multiple pulse width modulation or a single pulse width modulation, the equal pulse width will be presented. So if you go for the bipolar PWM technique, this type of waveform, that means unequal pulses you are getting. So for this, how to solve this, how to get the BN expression, that is very important. So first, if you take this waveform, right, and second one next, this is the waveform. So here, the first one is the positive half cycle you are getting obtained, and here negative half cycle you are getting, right? That is the difference between these two. Okay. Now this is pi by 2. Now see, pi by 2 minus theta is equal to pi by 2 plus theta. Therefore, simply it is a quarter wave symmetry. Right. When you are having quarter wave symmetry, if you do the integration 0 to pi by 2, it is more than sufficient. So therefore, Bn is equal to 4 by pi integral 0 to pi by 2 f of t sine n omega t. Okay. So here, what happens from 4 by pi? First, what happens 0 to alpha VDC sine n omega t plus alpha to pi by 2. So alpha to pi by 2, what happens? Minus VDC sine n omega t. If you simplify this expression, what you will get? Bn is equal to 4 VDC by n pi 1 minus 2 cos n alpha. In the similar manner, here what is the difference is here positive half cycle you are obtained, you are getting, and here negative half cycle you are getting. That is the only difference. So again, if you do the Fourier series, right, you will get 4 VDC by n pi 2 cos n alpha minus 1. Just reverse. Here it is 1 minus 2 cos n alpha. Here 2 cos n alpha minus 1. That is simply you can remember. If you remember this equation when you are having negative, just oppositely you just write it. That is sufficient, right? So next, if you take one example, right? So here this is pi by 2. So totally alpha 1, alpha 2, alpha 3 is available. Then I will give the shortcut method as well as regular method what we are discussing. So again, this is pi by 2 minus theta, pi by 2 plus theta is same. Therefore, it is odd symmetry. Then you have to go for only from 0 to pi by 2. Then if you go for 0 to pi by 2, write down the expression and finally you will get this one. Okay. But how to write down the shortcut method, that is most important, because this is less number of pulses. When you are having more number of pulses, if you do the integration means it is more complex. For that again we have shortcut method. So first what happens whenever you are having negative half cycle, just now we have discussed, whenever you are having negative half cycle, what happens? 2 cos n alpha minus 1. So like that, First you have to write down 2 cos n alpha minus 1. That is the first one, because here negative half cycle it is starting. So that's why you have to write down 2 cos n alpha 1 minus 1. Next, if you see here, this second one, alpha 2, here it is the waveform is changing from positive to negative. So at that time, what how to return minus 2 cos n alpha 2. Understand what I'm saying? Why minus means it is changing from positive to negative. So that's why minus 2 cos n alpha 2. Understand what I'm saying? Next, third one, what happens? It is changing from negative to positive. Therefore, what happens? Because of it is changing from negative to positive, I have to write down positive 2 cos n alpha 3. Right. So just add all these expression. So and you will get this one. Right. This expression is this term is same as for any case. 4vs by n pi, and this expression you have to write down. So whatever you are getting here expression, just write down. So instead of doing integration, right, you just write down this is a shortcut method, right? So this is the way to write down shortcut method for when you are having unequal pulse distribution. Okay, right. So now if you take now next derivation, if you go for what is the average output voltage equation, whether it is for bipolar or unipolar, the equations are same. So I am taking this the output voltage of unipolar, right? Therefore, what happens here? The duty cycle is changing. Duty cycle is nothing but on time. So on time is changing. See here, this pulse more on time, here less on time, and here very less on time, like that. Again, negative half cycle, the t on time is increasing. Therefore, how can you write this V naught if this expression VDC, because this magnitude is VDC into T on divided by T on plus T off. Therefore, what happens? V naught is equal to VDC, T on by T on plus T off is D. So in the 4th unit choppers, I have already discussed this one, right? But how you are generating this D in choppers? See, here you will get in choppers you are using this sawtooth waveform, and reference waveform is increasing like this. So therefore, automatically your duty cycle is increasing, right? So how can you write duty cycle? And another way is simply VR by VC. This is VR and divided by VC. VC is nothing but maximum value you have to write down. So that is nothing but your T on by T on plus T off, right? So instead of this D, you can write down VR by VC. This VR by VC, generally we are calling it as modulation index. Understand? So VR is nothing but your sinusoidal waveform, and VC is nothing but your triangular waveform when we are comparing the pulses. Okay, right. So this is for average output voltage equation, which is valid for unipolar as well as bipolar. Next, if you take in unipolar, you have one more equation, VAN. So that is nothing but VDC by 2 into modulation index, right? What is VA naught? VA naught is equal to VDC by 2 into modulation index. So why VDC by 2? You please refer the bipolar scheme, pole voltage. There you are getting VDC by 2, right? In the similar manner, VAN. So let me go for VAN once, right? So this is your VAN pulse. Why you are getting VDC by 2 means here it is 0. So sometimes up to this time is 0, and every time you will get only positive. You never get negative voltage. So like that, because of this is only positive, if you take in the average sense, automatically you will get this VDC by 2 only. Okay. So if you have VDC by 2, yeah. So because of VDC by 2, you are writing like this. Okay, understand what I'm saying? This pole voltage already have referred in bipolar scheme. You just go to bipolar. That pole voltage you clearly get this one VDC by 2. So please watch my previous video. Okay. So this is average output voltage equation, pole voltage, and VAN equation. Okay. So next one, now we'll go for one problem for this unequal voltage distribution. This one, I already told you how to write down this equation, right? So for this, first we will find out B1. So I have taken this alpha 1, alpha 2, alpha 3. For one particular simulation, I have taken this one. And what is this B1? 80.38. What is this B3? 0.93. And what is the harmonic factor? 1.1. And what happens this one? B5, this is minus 22.08, and you are having minus 27.4. right? So this harmonics is not, see B3, what is B3 means, just you substitute n is equal to 3, then you will get B3. What is harmonic factor? B3 by B1, you will get like. Similarly for B5 and B7, definitely will get it. Now if you observe the simulation, what I have done, so this one. So just now we have discussed this, you want previously just go once. So what is B3 harmonic factor? 1.1. Harmonic factor 5, what happens? 27.4. Harmonic factor 7, how much? 1, not 1.1. Please remember this one to just observe. So next slide. So here, what is the harmonic factor you got? 0.97. We got 1.1 percentage. Next, H5 is 27.4. Of course, very nearer. H7 is there. We got 109, 101, and here it is 102.36, like that. So some slight errors you are getting, but fundamental component B1, it is same. That's our answer. Right. So if you take next one, let us take, this is a bipolar, right? One bipolar problem I have taken. So first thing is, this is the values I have taken. Vs is equal to 100 volts. Reference voltage, sinusoidal magnitude, peak magnitude is 0.8 volts. Vc, peak magnitude is 1 volt. Carrier wave frequency 750 hertz, reference wave frequency 50 hertz. Find the output voltage, third harmonic and fifth harmonic magnitudes for a full bridge inverter using bipolar spwm technique. See, this is your bipolar scheme, right? So first of all, here what happens? Number of pulses, Fc by Fr, that is nothing but 750 divided by 50, which is nothing but 15 pulses per cycle. If you count from here, it definitely will get 15 pulses. That means one cycle. So this is one. So one time period means just count. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, like that. Okay, right. So what is you have modulation frequency ratio, right? That is nothing but Fc by Fr, which is nothing but same, right? This is the number of pulses or cycles we just consider, right? From one here you are getting one cycle like this, so that is nothing but 15 pulses per cycle. Okay, cycle means you just consider this one. So how many pulses mean? This is total one pulse you have to consider, right? So here this one, for this one I have written the shortcut equation. Just now I told you how to write the shortcut. Here how many angles are there? Alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7. Right, this is 90 degrees, this point, right? So for that I have generated, I have written the shortcut equation we are getting, right? And what is modulation index? VR by Vc. VR is nothing but 0.8, Vc is nothing but 1, we will get 0.8 volts. What is V0? VDC into modulation index. What is VDC? You got VDC value is, this value is 100 into this one, 80 volts. Okay. So by using this equation, you cannot find out V03, V05 like that. Definitely have to go for this equation, right? Now we'll go for the equation. I have substituted here. I got B1, this one. B1 is equal to how much? 79.59. So just observe here. This is the voltage, fundamental voltage. This is how much? 80. So just now I'm getting again from B1 also you are getting 79.59, almost same. Okay, so slight variation. But if you go for B3, 0.59, what is the harmonic? That is 0.0060. That means you will get some around 0.63 percentage in terms of percentage. So this is 0.82 percentage. This is some 29.16 percentage. This is 103 percentage. This is 62 percent. Okay. Now if you observe whether you are getting these values or not, that is most important. Let us go for HF17. HF17, how much you are getting? 0.62. If you go for with percentage, 62%. Now we'll see HF17, how much? 27.55. That is most important. So what is HF13? 29.16. HF13, 27.45. Variations are there. But fundamentally you are getting almost same. Okay. So here what is the conclusion I want to say is very, very important, this one. So this Bn expression is not suitable, right, to find out the harmonic component. Very important. Because see, in sine PWM technique, sorry, single PWM technique and multiple PWM technique, we got exact answers, right? We got exact answers every time. This b value is matching. But in sinusoidal PWM, this bn expression, whatever we are writing here, bn expression, so that bn expression, right, if you do for harmonic magnitudes, it won't appear. This is very useful only to find out the fundamental component. This is not useful. So why you are not getting means this one. These values are not matching with simulation result due to low frequency wave is comparing high frequency wave. So for this, what happens? You have to go for double Fourier series. We have to apply, right? Double Fourier series concept. Here we are using only single Fourier series. So whenever you want to find out the harmonic component magnitudes, this Bn expression is not sufficient. This expression is only to find out the fundamental component, right? So, but remaining voltage magnitudes, harmonic factors, if you want to find out, this is not suitable. Then you have to go for double Fourier series, right? So this is the one. This is the equations for double Fourier series, which I have taken from one high standard textbook, right? I will show that one, right? So that textbook is this one. 1 second. So here, this is the textbook, pulse width modulation for power converters. So D. Graham Holmes and Thomas A. Lipo, right? So from this textbook, this one, from this textbook, Thomas A. Lipo, right? From this textbook, you find out this equations. So that equations I will show 1 second. So this is the equations, right? So double Fourier series concept. So now we'll discuss this one. Okay. Actually, this double Fourier series concept, why you have to apply means when you want to go for this low frequency carrier wave comparing, then you have to apply. See here, if you want, you can see it carefully, right? So the essential concept of two-level pulse width modulation converter system is that low frequency target reference waveform is compared against high frequency carrier waveform, and the comparison of output is used to control the state of the switch leg. So with this reference waveform is greater than carrier waveform, the phase leg is switched to the upper DC rail. With reference waveform is less carrier, the phase leg is switched to lower. So the resultant leg is out is stream per pulse between the upper and lower DC rails. So as a fundamental component, the target reference waveform, but also incorporates a series unwanted harmonics generated as a consequence of switching process. So for this determination, what happened is we have to use double Fourier series. So in case of when you are going for single pulse width modulation and multiple pulse width modulation, so we didn't always we are using a DC signal, but this is AC signal. When you are using this AC signal, right? So some we have to go for another extra analysis. That extra analysis is nothing but this double Fourier series, right? So with this here, here I want to show what is extra analysis we require. So till now we have discussed B1 component. That B1 component is fundamental component. We have completed that, but we have to go for one more, which is called as carrier harmonics and sideband harmonics. What is this carrier harmonics, right? So actually, what is the MF value we got? 15. That MF is equal to 15 is nothing but your carrier harmonic, right? Carrier harmonic. See, M is carrier index variable. Already we have discussed MF. MF we got already 15. So see, this 15 is nothing but your carrier harmonic. Next, sideband harmonics. That means before this 15 and above this 15, you are having some harmonic components. Because of this carrier harmonic, you are having some sideband harmonics, right? So till now we didn't get exact answers. That is the reason behind this one. We are not adding this carrier harmonic as well as this one. We are only solving this one. Forget about this DC offset. We are always solving only this one. But you are not adding this components. So that's why you are getting some error. So every time, see, every time if you want to do expressions it will be more complicated. It will be more complicated because let us go for just 1 second, right? Yeah, here how many pulses you are getting? 15 pulses. So because of 15 pulses, because of odd symmetry, so you are having some alpha 7, you are having this big equation. Let us say my carrier frequency is 1500, right? Therefore what happens, it will be doubled. That means you will get alpha 14. Then at that time this expression is complicated. So only to solve this fundamental you are spending more amount of time. Then when you simplify this one as well as this one, so it will be more complicated. So for that, these textbook people only, right, they have done some analysis, right? So they have done some analysis, and finally they have given this this graph they have given. So for particular MF ratio value and with the modulation index, right? So they have given some constant values. Based on these constant values, based on this all these constant values, based on these constant values, we can find out the whatever the harmonic component, you can find out very easily. So here, this is the thing I want to say. Whenever you are using this BN, only this fundamental component, you will get some errors. To overcome that problem, we are using this carrier harmonics and sideband harmonics equations also. So firstly, when you are finding any problem, just find out the fundamental component. Forget about this one. So by using this graph, what they have given, we will have one table. Based on that table, we'll directly find out. I will show that one. Right. Now we will have idea about what is carrier harmonic, what is sideband harmonic. Right. So the carrier harmonic will be obtained based on your MF ratio only. If MF ratio is 20, so this 15 is up. I mean, this carrier harmonic is appeared at 20. If it is 30, it will be appeared like. But sideband harmonics will be appeared based on carrier harmonic formulas. Okay. So now this is the table. So this is the modulation index. Based on this modulation index, you have these values. This is MF. Now what is the value of MF? In our problem is 15. So these are the sideband harmonics. MF plus or minus 2, MF plus or minus 2. So based on this value, we are using now 0.8 modulation index. For 0.8 modulation index, for MF, what is the value? 0.01818. So sorry, sideband harmonics, what is the value? 0.220. Okay. So based on this, we will find out that. Okay. Now we'll look into this. So again, I have taken this problem. So FC is same, FR is same, remaining values are same. Now we have to find out the first and second band of harmonic magnitude, right? So from this, here, what is the first band of harmonic? MF. What is the second band of harmonics is this one, 2MF plus or minus, right? This is the first band, this is the second band of harmonic, okay? Right, now, so what is MF? This is 15. So first band of harmonics, what happens? MF plus or minus 2. So that means 15 plus or minus 2, that may be 17 or 13. First we will calculate V013, which is nothing but VDC into MF plus or minus 2 at 0.8, because our modulation index is 0.8, because VR by VC is nothing but modulation index 0.8. Okay, VDC is 100. I have given this VDC is 100 here, right? And MF plus or minus 2 at 0.8. What is that value? MF plus or minus 2. MF plus or minus 2 at 0.8. What is this value? 0.220. So that value only I have substituted here, and finally what I got? V013 is equal to 22. And what is HF13? Is nothing but 27.5. Okay. Now, what is this 17? So VDC into MF plus or minus 2 at 0.8. Again, see, whatever you are having this 17, you will get the same value here, right? So whatever 22 you are getting, here 22. So for the next problem onwards, just solve only one value, and for the second value, you will get the same value. Okay, same answer. Next, what is V015? So VDC into MF at 0.8. Now we'll see what is the MF at 0.8. MF at 0.8 is 0.818. Okay, so 100 into 0.818, which is nothing but 81.8. What is HF15? 81.8 divided by 80, which is nothing but 1 or 2%. Next, second band of harmonics. I'm sorry, this is second band of harmonics. It's not a first band of harmonics. The second band of harmonics is 2mf or plus or minus 1, 2mf plus or minus 3, like that. So second band of harmonics is nothing but 2mf plus or minus 1 into 2 into mf is how much? 15 plus or minus 1. Therefore, what happens? This second harmonic will be appeared. One is at 31, another one is 29. Okay. So let us go for this one, 31. V naught 31 VDC into 2mf plus or minus 1 at 0.8. VDC is 100. 2mf plus or minus 1 at 0.8. 2mf plus or minus 1 at 0.8. How much? 0.314. So 314, and you will get V0 314 31.4. So you'll get the same equal to V0 29. So how much you got? Some 39.25%. This is for second band of harmonic, 39.25, right? So now what happens again? Next one is for 33. Second one 33. How much you got? 17.37%. Understand what I am saying? So now we will see this one. So first, what is the value of 13? 27.5. So what is the value of 15? 102%. Understand? Now we'll see this value by using your sine PWM technique. Okay, along with this, I will also go for pole voltage. What is this pole voltage? Just earlier I have discussed what is the pole voltage formula is VDC by 2 into modulation index. What is VDC by 2 means? 100 by 2 into modulation index is how much? 0.8, right? So 0.8 into 50 means what happens? 40 volts you have to get pole voltage. You please remember this. And what is the fundamental output voltage we got? 80 volts. Understand what I am saying? Now we will go for the simulation. Then you will get one clarity, because in the last class I didn't shown this bipolar concept. In this bipolar concept, we'll discuss this. First, I will run the simulation. Right now, first of all, whether what I have kept it is correct or not, I will show. This is a modulation index 0.8 reference wave and carrier wave. Carrier wave magnitude is 1 or minus 1. Peak value 1 or minus 1. So modulation index means what happens? VR divided by VC. What is VR value? 0.8 divided by VC value is 1. So this is the voltage, right? Now we will go for the output voltage equations. Understand what I'm saying? I mean, sorry, output voltage waveforms and all those things. So, and harmonics. So this is the FFT analysis. Right, 50 hertz. Wait 1 second. Yeah. Now, what is the fundamental voltage? Now we'll go for first list. So what is the list? We have fundamental is 79.97. Okay. So what is the 13th harmonic? 27.45. 15th harmonic is 1 or 2. We got 17th harmonic is again 27.55. Remember this 27.45, 1 or 2, 27.55. Just 1 second. Again, we will come back here. So here. See this 27.5, 1 or 2, again 27. The same thing just now what I have discussed with you in the simulation point of view, what I am getting is this one only, right? So 27.45, 1 or 2. So exactly we are getting. Compared to your the BN expression, these values are giving more accurate. Okay, right. Now first band and the second band I have to show, right? So what is this first band and second band, right? If you go for the bar and you will get some. So this is the first band of harmonics. First band means where you are getting first band at MF is 15. Second band, what happens? 2 MF plus or minus 1. That means 2 into 15, that means 30 plus or minus 1. That is 31 or 29. See, 31 or 20. Right. So next 2 MF plus or minus 3, some values are there. Those values are this. So that means here this is the what happened, what is the value I want, what is this one I want to say is first band of harmonics. This is a second band of harmonics. Understand? Next, coming to right. So the pole voltage, right? So this is a pole voltage which I want to show. See the pole voltage magnitude, what I said, VDC by into modulation index. What is VDC by 2? So 100 divided by 2 is 50 into modulation index is 0.8. So 0.8 into 50, how much? 40. So this is almost 40. So this is about, so this is about what I want to say for the simulation of this bipolar scheme, right? So, so now the same problem we have to apply for the unipolar scheme. The same problem you have to apply for the unipolar scheme, right? So in unipolar, what is the difference? Just one is output frequency is double. So that means your first band of harmonics is started from 2 EMF plus or minus 1. Simply. Okay, this is the thing I want to say. Therefore, what is this first band of harmonics is 31 and 29. In case of bipolar, what is the first band of harmonics is 15, 17, 13 like that. Second band is 31 and 20. Now this second band of harmonics will be the first band of harmonics in unipolar. See, this is I said that this is a wrong one. This is a second band of harmonics. Okay. In case of unipolar, this because of output frequency is doubled, so that's why you are getting the second band, first band of harmonics is 2 EMF plus or minus 1. But your fundamental output voltage is same, pole voltage is same. It won't be changed. Understand what I am saying? So if you solve these ones, I have already solved each and every equation. Right, you will see this one. Right. Now here for the first band of harmonics, this what is this H of 31? You are having 39.25%, and this is H of 33, 17.7%. H of 35, we are having 1.65%. Right. So here first 31 and 29. 31 how much? 39.25. 33 how much? You are having some 17. Next 35 how much? You are getting 1.65. Right. In case of bipolar, what happens? First band of harmonic is how much? 1 or 2%. Therefore, the filter size increases simply. Whereas in case of bipolar, the first band of harmonics harmonic factor is how much? Maximum is 39.25. Therefore, filter size is reduced. So that's why for single phase inverter, it is better to use unipolar scheme. But what happens? Two signals are required. Two reference signals are required. In case of bipolar, only one signal, one reference signal is required. So I already shown the MATLAB simulation of unipolar in the last class. Of course, again I will show it. Right. So now, if first we will run the simulation. Okay. So we'll run the simulation. Now you'll see here the two carrier waves. Right. So two reference wave, not carrier waves, two reference wave. This is the first reference wave. Having the phase shift is 0. Second reference wave, what happens? Phase shift is 3.14. That is nothing but 180 degrees radians. In terms of radians, 3.14. Two things are there. And this is only one carrier wave. But what happens? Two places we are using. Okay, that I have already shown you in the last class. So this is the screen I want to share. This is the two waves. So this is 0 degrees. This is 180 degrees. Right, two waves we have to show it because two reference waves are required to generate the pulses. Okay. So and coming to the harmonic analysis. Right. So first we will go for a unipolar output of unipolar. Right. So output of unipolar, if you see. Yeah. So here, what is the first band of harmonic at 31? I think where it is. Yeah, 31. See, this is the 31. So this is the 31 first band of harmonic, some around 29 and 31 like that. So just now I have shown you. Right. If you want, again I will show this. 1 second. So first band of harmonics you are having 31 and 29, right? Both magnitudes are same. See, 31 and 29. What is the percentage? 39.25 percentage. That 39.25 percentage. 1 second. Yeah. So see, the 39.25 almost same like that. Okay. Second one is 17.5. Okay. So what is the fundamental magnitude? 80.01, which is same in bipolar as well as unipolar, right? Coming to the pole voltage, what is this pole voltage? This one, the pole voltage. Again, you are getting the pole voltage magnitude is 40.01. Modulation index is 0.8. VDC by 200 by 250. So you will get the same thing. So it never be changed. Okay. And if you go for in terms of bar, let me go for 1 second. So see, so this in the bar means we have to go for output voltage. Right? Where is the first band of harmonics exist? 31 and 29. In case of unipolar, 15, somewhere around here. So that's why the THV is reduces here. In case of bipolar, so what is the THD got? 145 point something, 145 point something you have. So because of that reason, right? So generally we don't go for unipolar scheme. Some cases. Okay. So this is the final. Just I want to conclude now. So therefore, what happens? This is 145 and this is 76. That is a major advantage. So unipolar scheme. So here the first band of harmonics is exists at 15 and here 30. That means if you go for unipolar because of output frequency is double, then what happens is filter size is reduces. Why the filter size? Why you are getting this one and why the filter size is that this means THD is less. The THD is less that I have shown that error. The error in case of 1 second. Yeah, in case of unipolar scheme, the output voltage changes from 0 to VDC, right? So or 0 to minus VDC. So at the instant energy, error is reduced. Whereas in case of bipolar means this one. Bipolar means this is VDC minus VDC. So change in error is very high. So due to that reason, generally we are not prefer the bipolar because of that error. What happens is more THD will be presented in the system. Okay, because of that, 1 second. So because of that reasons, it is better to prefer unipolar scheme, right? And the fundamental voltage magnitudes are same. Okay, only THD variation and output filter size is reduced. So due to some advantage only, you have to go for this unipolar scheme. This is about this one. And the major important today's topic, what I have discussed. Yeah. So I have discussed, I said that clearly. Again, I want to say this important point. This Bn expression is valid only for to find out a fundamental component. This is not valid for to find out the harmonic factors because these harmonic factors will not be these harmonic factors are not same as that of your practical values. So because I said that you have to add some carrier harmonics as well as sideband harmonics, then only you will get the exact values. Okay, so this is about your sine PWM, right? So but uh, this sine PWM. So here, for the examination point of view, you just write down this bipolar scheme means, 1 second, just write down this bipolar scheme means, I just write down this one as well as this, and the unipolar scheme means, 1 second. So this one unipolar you can write. For bipolar, these two will get right. And write down some equations what I have just shown. The equations. Uh, yeah, this one. This is the equations for output voltage. This one. So this is sufficient for the examination point of view. But why I have discussed means this concept is very important. So just write down this bipolar scheme is this one, as well as this one, as well as this some output voltage equations. Where is that? Yeah, this output voltage equation you can write down. So because why I have discussed in the detail, for the next year you are going for the major projects. At that time, power electronics people generally suggested these techniques, which will be very useful. So for your major projects also. So that's why I have discussed all those things. So in this class, I have completed SPWM perfectly, and PWM total PWM control techniques I have already completed. Right. So in the next class, I will discuss the series inverter and parallel inverter.